Hello, and thank you for joining Maplesoft's Virtual User Summit. My name is Shola Slough, Technical Communications Specialist at Maplesoft, and I'm your host for this presentation. The presenters for this session are available in the Communication Lounge from 3:30 to 4 p.m. for a live chat on the day of the event. So please head to the Communication Lounge and select the appropriate scheduled chat for this presentation to ask any questions you may have. If you are viewing a recording at any other time and have questions, please leave them on the message board in the Communication Lounge and a Maplesoft representative will get back to you. This session is titled, Bringing Excitement and Relevance to High School Math. In this session, high school educators will show how they use Maple to engage their students, help them learn new concepts, allow them to solve real-world problems using only the math they already know, and give them an enticing glimpse into the type of math they will see in college. Maple can even make students say, "Wow, that's really cool," once in a while. Let me now introduce our presenters. Calvin Armstrong is a mathematics teacher and Director of Teaching and Learning Innovation at Appleby College in Oakville, Canada. He is also on staff at the Park City Mathematics Institute, a program of the Institute for Advanced Study, where he works with teachers from around the world to improve pedagogy and coach future mathematics education leaders. He has been an enthusiastic user of Maple since his time in university. Jason Schattman is a high school teacher at Sir John A. Macdonald Secondary School in Waterloo, Ontario. He earned his PhD in Operations Research from Rutgers University in 2000. Jason worked as an applications engineer at Maplesoft until 2004 when he decided to switch and go into teaching. His mission as a teacher is to help his students appreciate both the beauty and the utility of mathematics in everyday life. The final presenter for this session, Scott Hagan, is a math instructor at the British Columbia Institute of Technology in Vancouver, where he currently teaches math to mechanical and civil engineering students. He earned his PhD in theoretical physics from McGill University in 1995. And from the beginning of his teaching career, he has made it his goal to always make it clear to his students why they are learning the math he is teaching and how it is relevant to them.
Hello, folks. My name is Calvin Armstrong. I'm a mathematics teacher at Appleby College. Appleby College is a grade 7 to 12 independent school. And what I'd like to talk about today is how we use Maple TA for assessment as learning. Our situation was that we had a huge increase in the number of students taking calculus, and indeed all other advanced math courses. The requirement for universities has increased, and so we have a lot more students who really do need to have that calculus credit. As a result, we had students who may not have been as prepared as they once were coming into calculus, and we had students who wanted to take the advanced courses that had external exams, which is really something that we're not familiar with in our jurisdiction. For us, we found we couldn't get the results quick enough using pencil and paper, and very often the teachers wanted to spend time in class not on the assessments, not on the feedback that would require immediate, let's try that again. The teachers didn't want to spend class time on the assessments. They didn't want to spend class time on doing all the pencil and paper work. They wanted to spend time in the classroom doing things that would have the students collaborate and discuss. The research all pointed to the fact that too much time was spent in classrooms on simple questions, that there wasn't an opportunity to move beyond the plug-and-chug problems of the textbook and really get deep into meaningful questions. Our students are very busy, so they tended to be away, they would be sick, they would go on exchanges, and in today's age, parents are much more involved in their students' mathematical careers. That being said, they don't always know how to do the mathematics that the students are being asked to do. In our jurisdiction, we also have the increased perspective on assessment, and there's a distinction between assessment for learning, what the students would say it doesn't count in the gradebook, but it does provide them feedback on how they're actually proceeding in class, followed by the summative assessment of learning, where the students are actually being given a mark inside the gradebook. The distinction between the two is that the formative actually is what makes learning available to the student. The summative is too late in the learning cycle, and they don't actually produce much learning as a result. The motivating factor for all of this was the pivotal research article Inside the Black Box by Black and Willem. And it was that formative assessment was really the only thing that made a difference in a student's learning. Everything else, classroom size, technology, was completely irrelevant if there wasn't the presence of formative feedback. So our solution. After a great deal of searching, we came across MapleTA. We were familiar with Maple as a result of using Maple in mathematics classrooms. It's a great tool. The students love being able to explore as real mathematicians. And so adding on the additional factor of the assessment portion only seemed to make sense. It was nice. It was web only, so there was nothing additional for the students to add. They would go into any web browser and immediately begin to use the assessment program. It came pre-prepared with some questions, not just multiple choice, but also the additional aspect of the free response. Mathematics is not well assessed by multiple choice. Being able to actually enter an equation, enter a graph, enter actual mathematics is a huge step forward when it comes to online assessment. The other nice thing was that we could add our own questions. It's very limiting to be just given questions that don't match the way you taught the material. It doesn't match the way you would assess the material, and it doesn't use the language or notation that the students and you are familiar with. Most of the online assessment we ran into were just giving numeric responses. The student would calculate and enter a number. It goes back to the plug and chug that we ran into difficulties with every other assessment. And most often, they only had multiple choice. That's far too limiting. So, as an assessment tool, MapleTA gave us the opportunity to enter anything. The fact that it could even provide the student response of a sketch was something that we hadn't seen before. As a tablet school, a school that has every student with a tablet computer, the ability for the student to use their pen and actually sketch out the curve that they wanted to put as their answer was remarkably powerful. For use in science, the ability to understand the difference between units and convert between them so that if a student entered 10 centimeters, they would actually be marked correct if the answer were 100 millimeters. It accepts algebraic input and understands what that means. So a student would not have to necessarily use the word simplify to provide a response. So if the student had entered 2 times bracket x plus 3, they would be marked the same as if it were entered 2x plus 6. Any other online tool would have marked either one of those wrong depending upon what it was programmed to accept. So the opportunity for the student to actually do mathematics and have the system understand the difference between the two answers is remarkably powerful. The simplest part of MapleTA was, of course, the multiple choice. But the power within the multiple choice is that every one of the digits of the question is generated algorithmically, and the responses are generated as a result of those initial algorithms. So once a teacher developed a standard template for a question, they then had almost an infinite number of possible questions with randomly determined questions and answers. And that gave tremendous power for students who were trying to develop algorithmic facility with the mathematics. Similarly, with questions that required free responses, all of the digits involved with the question are algorithmic. So the students could evaluate the integral between 4 or 5, but the next time they came to the question, it would be between 7 and 8 of ln 3x. And so although the algorithmic question would be different, the student work would eventually notice to be the same. In the same case with a question that involved true or false, each one of the digits are randomly assigned, and so there are essentially an infinite number of questions the student could be asked. We have an example here of different ways the student could have responded with algebra, and either way the question would have been marked correct. And for a student beginning to learn about algebra, that's incredibly powerful. Too much negative feedback is given when a student writes something that is mathematically correct, but an automated system doesn't mark it so. When we move up into the calculus, the ability to ask questions that involve algebra. Again, most of these would have been asked as a multiple choice question on any other automated assessment system. But now they can be asked as algebraic response. And again, we're looking at randomization, that these numbers here, and indeed even sine and cosine, could be changed as a result of the template of the question. Antiderivatives as well. And you see there an example of how each one of those answers is mathematically correct and will be marked mathematically correct. And you can imagine as a mathematician all the different opportunities that the student could actually respond with that are all indeed correct, but any other system would not be able to understand that the mathematics is actually correct. When we enter graphs, the student can actually sketch the curve by putting down points and providing us with a curve that is increasing and concave up. And the power here is that the teacher has to do almost nothing to provide that. Almost any other assessment system, you would almost have to have that pre-programmed by a professional programmer. The teacher just has to ask for a graph sketch and continue on that way. It's a remarkably powerful way of actually testing for understanding of graphical knowledge. What we found as well was that not only would they know whether the answer was correct, but we could provide ways of describing how they should have started to format the answer. What we're looking for is feedback to the student in a way that is meaningful to them, not just that they got the right answer, but how they might have wanted to proceed to the question. And again, I always want to point out that all these numbers here are randomly assigned, and the answers are actually correct for the numbers that have been given in the question. As a teacher that has not a lot of time on their hands, once I have this template made and with these algorithmically designed, I have an infinite number of questions available to share to my student. And there you see one for factoring by decomposition, and all these numbers here, of course, are changing, but because the algorithm is there, the student sees the correct solution regardless of the initial question. What was really interesting was that factoring, of course, is a skill that some students find quite a bit of a challenge with. But because they had access to an infinite number of questions, and because the actual grades aren't recorded at certain stages along the way as a result of teacher choice, the students began to game the system so that they would game in competition with their peers over who was getting the best scores, whether they could answer 10 in rapid succession. And so the excitement factor of factoring went up considerably. They weren't just doing dry paper sheets of factoring, they were actually engaged on a computer in competition with their peers. And again, there you see the actual process of how we would have gone over the factoring, as well as a link to a short video on factoring so they can see an actual person working through the problem on a tablet computer, much as you might see on Khan Academy. So the ability to add in video and links to resources within the answers really does sort of support not only the student, but again, parents tend to be more involved nowadays. They don't necessarily remember factoring, so as a reminder to the parent on how to factor, those resources become remarkably handy. Hints can be included within the test itself rather than at the end of the assessment, and the same thing can be added within the hints. We tend not to use hints within the actual question. Rather, we want to do it as feedback after the fact. Everything is done algorithmically. We have very few questions that are just one-offs, so that the student always has the opportunity to go back and practice with different numbers, and as you'll see momentarily, with actual different situations. So in terms of inequalities, very often students have difficulties with open and closed sets, and so these are drawn within a graphics program. MapleTA passes on the numbers algorithmically to the drawing program. The drawing program draws a number line, opens and closes a set, and of course the numbers here are all dependent upon the values. In algebra, for us, often we would just give them the system and ask for the answer, the intersection point. Of course, we want to know intermediary steps. And because MapleTA will allow the student to enter algebra, we can actually follow through along the question and actually show them the intermediary steps. And MapleTA will mark each individual step and then give an overall mark as well. And so the student is beginning to see where they're making their errors and at what step. We can get pretty complicated, lines of best fit. Geometry, again, we pass these dimensions off to the drawing program. The drawing program creates the image, passes it back to MapleTA. The student can put in the number and the units have to be correct based upon the problem that is given. If the student enters it, if you have a very bright student who changes millimeters cubed into milliliters, the system will be able to understand it and mark it correct. In geometry, students are often perplexed by the rotating opposite and adjacent within trigonometry, and so we not only wanted to make sure that they had a chance to see the triangle, but because it's all algorithmic, we wanted to make sure the triangle rotated so they didn't get used to it always being in the lower right-hand corner, but that sometimes angle K was over on the left-hand side as well. And so the algorithm not only provides different values, but also reorients the triangle so the student is not used to the same arrangement each time. Again, students begin to game that system and want to see how many triangles they can get in a row. We can get nice complicated diagrams, and again, that they're labeled appropriately, and again, randomized. Relatively complicated in terms of the situation, but all these numbers are changing, so even if the diagram is reused, they see different values and have to work it out. And in calculus, this goes back to the power of the underlying Maple system. The students are used to, when they're talking about calculus, using Maple to actually visualize three-dimensional objects. And so seeing that same thing in their assessment is a nice feedback mechanism for them. They've seen this before using Maple in class, and so they see the visualization in an assessment. On paper, that's very hard to do in black and white. On a computer, of course, you have the vividness of color and the opportunity for them to actually see what's going on rather than try to visualize it themselves. We then go on to additional aspects of calculus. You'll notice that the highlighted areas are all based for a integration question, but because it's Maple sitting in the background, a car is the same as a motorcycle and is the same as a truck. So we're pulling that information from a list. The student sees a different context. And because we're dealing with students undergoing an assessment, they will more likely talk to each other about the problem and the comparison between individual sections. They're talking about a motorcycle question, they're talking about a truck question, and so there's a less opportunity for them to cheat when they're talking about assessments with their peers. And of course, as a feedback mechanism, they have the opportunity to revisit a situation. And what we did was we made the motorcycle, whenever a motorcycle was chosen within the algorithm, the numbers were higher. A motorcycle will tend to accelerate faster or more quickly than a truck. And so we tried to make the situation more realistic. You always want to try to bring in the reality of the situation involving the mathematics. We see again the power of Maple in this type of question with slope fields. Almost any other assessment tool, first of all, would not be able to produce this algorithmically, but also create such a vivid diagram the students can use to evaluate the system. The fact that Maple, the Maple that the students know and love from working on it in class, is brought forward onto the assessment and is a power of the teacher that really no other assessment tool, from paper to anything online, can ever really adapt. The fact that every single student can have a different slope field, or every student can have as many slope fields as they want until they begin to see how the patterns are evolving. That's something that you really can't do. You can't photocopy enough slope fields to match what is capable with Maple and MapleTA sitting on the student's computer. So what we saw, and what we saw reflected in the research, that even the lowest achieving student, when provided with a structure like this, allowed it to improve their scores. And the initial hurdle they got, that they got it wrong, was fine because they were doing it in an anonymous situation. So no one knew how many questions they got wrong. And it was only after a long period of time when we said, okay, now we're going to look at actually recording a mark. They had all this time to actually try and change and challenge and improve. And what we saw was they would actually come in with screen clippings of problems that they tried and wanted explanation from. They would email the screen clippings to their teachers and look for feedback. So a very powerful tool, and really helped not only the high end but the low end to try to improve their value, their scores. We used it for all reasons of purposes, the homework check at the beginning of class, all the way through to exam review, and of course anonymously. We would have a huge collection of questions from around the year, and as we approached the exam we would have one random question. So they would walk up to the computer and ask for a random question, and it would pick any one of them from the curriculum. Practice after practice after practice in middle school when it came to integers, an infinite number of questions without limit. And this value of sustained practice, it's that reaching towards mastery that Maplesoft has built in. A student can go back in as many times as they want without any hint that they are not reaching success until they actually reach success and then surpass it. And the fact that they started to game the system, they started to compete, was really quite interesting. We don't often see that in mathematics. We don't have a retest policy because they have the opportunity as much as they want beforehand. They know going in that they've had a chance to see almost every possible question as part of their revision. So we find that our students do a lot more questions. They ask a lot more questions because they've seen a lot more questions. They get competitive when it comes to the mathematics, and they really like getting the right answer. They celebrate the fact that they went through and got 100%, and they really like getting the wrong answer and that no one has noticed. No one has had to mark their paper. No one has had to write something, acknowledge that they made a mistake. The machine has just told them, Maplesoft has just told them what their mistake was and how to correct it. And of course, as teachers, we like to track to know what they're doing and how they're doing it and what questions they're doing. Maplesoft tracks everything for us. We know what questions the student has done, what questions the student has not done in a non-formative, non-structured, non-assessed, non-threatening back space. So we asked our kids about using Maplesoft, and what we found was that they really did like getting that immediate score. They didn't like waiting for a test. They wanted to know immediately how well they'd done and how they could improve. They liked the fact that they were aware of how they were doing. They didn't have to wait a week, 2 weeks for the unit test. And they really did like that it helped them understand what they were doing and how they could improve. We have been really impressed with Maplesoft and the effect it's had on our math program, and we really look forward to the steps that are changing as Maple continues to improve. If you have any questions, I look forward to hearing them.
Good afternoon. I'm Jason Schattman, and I teach high school mathematics in Ontario. In this presentation, I'm going to show you how I use Maple graphics to help students understand distance, speed, time relationships in grade 9 and trigonometric identities in grade 11. My approach is to take a standard diagram that you might find in a math textbook and turn it into an animation that the students can manipulate. This gives the kids a much richer understanding of the mathematical relationships that the diagram is trying to convey. I'll start with an example application from grade 9. In this unit, students are learning how the formula distance equals velocity times time relates to slope and y-intercept, and how to interpret a distance time graph. The application is the mathematics of stealing second base. So in this application, we imagine that there is a runner on first base, the pitcher has the ball, and the pitcher is about to throw the ball to the batter at the catcher, and at the moment that the pitcher releases the ball, the runner on first is going to attempt to steal second base. When the catcher receives the ball, he's going to throw it to second base in an attempt to tag the runner out. Here's the model. On our baseball diamond, we're going to let D represent the distance from home plate to the pitcher, and D times the square root of 2 will be the distance between the bases, and 2D represents the distance from home plate to second base. T is going to represent the time elapsed since the pitcher begins his windup. Capital T will be the time at which the pitcher releases the ball. V will represent the pitcher's and the catcher's throwing speed. For now, we're going to assume they're equal, but later we'll allow them to be different. And D is the distance from the ball from home plate to the pitcher's mount. What I've done here is created a piecewise function using Maple Mathematics that represents the distance of the ball from home plate at any time t. When I evaluate it, the function looks like this. Between the time that the pitcher released the ball and the time that the catcher receives the ball, the distance is at d. I'm sorry, that's the time while the pitcher still has the ball. After he's thrown the ball, the distance is d minus the velocity times the time that's elapsed since he released the ball. When the catcher has the ball, the distance of the ball from home plate is, of course, 0. And then, while the catcher is throwing the ball, this is the expression, where v is the speed that the catcher is throwing the ball at. Now that I've constructed this, I have used Maple Graphics to graph this expression as a function of time. So we have the vertical axis representing the distance of the ball from home plate, and the horizontal axis represents the time since the pitcher has released the ball. This is a standard diagram that you might find in a mathematics textbook, and what's different here is I can click on it, and I have structured it so that I can change the speed at which the pitcher and the catcher are throwing the ball. So if I now drag this, I am effectively changing the slopes of these two non-horizontal lines. So what I'm telling students is that during this interval of time, the pitcher is winding up, so the distance remains constant. At this moment, the pitcher throws the ball, and the ball is traveling towards home plate. At this point, the catcher has the ball, and he's winding up, getting ready to throw the ball to second base. At this point, the ball is en route to second base, and at this point, the second baseman has it, and it stays constant at 60 meters from home plate. And what I'm doing here is changing the throwing speed of the pitcher and the catcher. And as their speeds increase, we notice that the time at which the ball lands at second base becomes shorter. So as they get faster, we can go from as little as 6 seconds to as high as something that's off the screen. Now what I'd like to give kids control over is not just the throwing speed of the pitcher and the catcher, but also the speed of the runner and the time that it takes the pitcher and the catcher to wind up. The goal of all this is we're going to be using mathematics to help the baseball coach make his team better on defense. What I have on the right side is a diagram. The red represents the same picture that I just showed you before, but with more controls. So here we can control, for example, the pitcher's wind-up time. So as I drag this, we notice that this point right here can be moved horizontally left or right. So if the pitcher's taking up to 3 seconds to release the ball, the runner has a 3-second head start during which to run. I can also control the pitcher's throwing speed as before, but now notice that is only affecting this slope and not the second one. I can change the time that it takes the catcher to release the ball, and notice this does not change the slope, that only changes the time at which this line begins its upward rise. We can also change the speed of the catcher's throwing, like so, and we can change the speed of the runner, and this brings us to the blue curve. The blue curve represents the distance of the runner from second base. When he's on first base, he is 30 meters away. I'm sorry, his distance from home plate. At this point, he is 30 meters away from home plate. When he reaches second base, he is 60 meters away. And how do we interpret this? If the blue line arrives at level 60 before the red line does, the runner is safe because he got there before the ball did. However, if he were too slow, then the ball gets there before he does and he is out. What I want students to get out of this is which of these controls matters the most. Let's suppose the pitcher's wind-up time is constant at 2 seconds and he has a constant throwing speed. Let's look at the difference in what matters more, the catcher's wind-up time or the catcher's throwing speed. If I move the catcher's throwing speed as low as it can possibly go, then it takes 6 seconds for the ball to reach second base. If I move it to 45, then I've only reduced the time by less than a second, like 0.8 seconds or so. Now let's put it somewhere in the middle. However, if I change the catcher's wind-up time, I can drastically change the time at which the ball will arrive at second base, which tells me as a coach that the catcher's wind-up time is much more important in determining whether the runner's out than the throwing speed. I can't do anything about the runner, but I'm just going to assume he's at a constant, let's say 6 meters per second. So what would I tell my kids? First I would ask them, whose throwing speed matters more, the pitchers or the catchers? Well, let's take a look. We saw that the catcher's throwing speed can only move the total time by about 0.8 seconds. Let's do the same thing with the pitcher's speed. At the minimum, it looks like we're almost at 7 seconds, and at the maximum, we're still at about 6.5. So the pitcher's throwing speed can only change the outcome by about half a second at most. The catcher's was slightly more. And I would ask kids at this point, why does the catcher's speed matter more than the pitcher's? And I'm hoping that the kids will figure out that the catcher has a farther distance to throw than the pitcher does. So the catcher is trying to throw a ball across a distance of 2D, whereas the pitcher only has to cover 1D, so there's more potential time savings here if the catcher can throw fast. So that's question 1. More important, suppose I'm the coach and I only have an hour to work with the catcher. What skill do I drill him on? Fast throwing or fast ball handling? And what I've seen from my mathematical model is that the catcher's wind-up time makes a much larger difference in the outcome than the throwing speed does. So that tells me as a coach that I'm going to drill my catcher more on getting rid of the ball fast rather than throwing hard. Now the bigger conclusion. What I really want students to take away is this fact, that mathematics can help us make decisions. As a coach, I made the decision to spend my time working on the catcher's ball handling rather than his throwing. But in general, mathematics is going to help me make all sorts of decisions, whether it's in business or personal life or science and engineering. That's the big lesson that I want my kids to take out of this. And I only arrived at these conclusions by being able to manipulate a diagram with controls. If all I had to work with was this diagram in a textbook, it would be much, much harder to make that point. At this point, I'm going to move to grade 11 and show you an application on trigonometric identities. Students hate trig identities because they're difficult, they're abstract, and it's very difficult to see the purpose of them other than pain. What I'd like to do in this is use some animated pictures to illustrate what a trigonometric identity is and how it can have a real use in the world. In addition, we'll also be able to use a diagram to identify new identities that we didn't know before. This is a typical diagram that you'll see in a lot of textbooks. It's showing the unit circle here, and it's portraying the relative relationships of the 6 trigonometric ratios: sine, cosine, tangent, cotangent, secant, and cosecant. And what we're going to do in this Maple worksheet is use animations to see why these relationships hold and why this particular picture is an accurate portrayal of these 6 ratios. Let's look at sine and cosine first. In this package here, I have written a short Maple procedure that will generate the unit circle and the relevant ratios for any ratios that the teacher wishes to choose. So in this particular case, we've taken the sine and the cosine, and when I click on this animation, I can change the angle. So as I drag this, we are changing the angle that is formed by this dot on the unit circle, the origin, and the horizontal x-axis. So as I change the angle, I can see how the sine and the cosine relate. And what I notice, and what I want my kids to notice, is that these 3 form a right triangle all the time, where the sine represents the height of the triangle, cosine is the width, and the radius is a constant 1 because this is the unit circle. And kids should right away be able to spot this identity. By the Pythagorean theorem, the sine squared plus the cosine squared must always equal 1. This is a squared plus b squared is c squared, where this is the hypotenuse. This one is usually pretty easy for students to grasp, even if we don't have an animation. But now the discussion gets richer. What is the slope of the red line? This is a nice segue into the tangent. I'm hoping that my students will realize that the slope of the red line is the difference in the y divided by the difference in the x, sine over cosine, and I'm hoping they'll say, oh yeah, that's tangent. But now this is where things get really interesting. Let's take a look at the same picture where I've added now the tangent. So why is this vertical line here representing the value of the tangent? Well, we saw that the slope of the line is equal to the tangent, but if you multiply a slope by an x value, you get a y value. Well, what is this x value from the origin to the edge? Well, that's just 1. So to get this y value at the tip of the red line here, I'm multiplying the slope, the tangent, theta, times an x value of 1. Theta times 1 is just tangent. I'm sorry, tangent times 1 is just tangent. And so that is why this turquoise line represents the height of the tangent. And I can just tell my students that, or better yet, I can sort of draw it out of them in a Socratic lesson and hope that they can come up with it themselves. Not only this, but now we can understand some other relationships as we let theta change. So what's happening here as theta approaches 90 degrees? Well, I can't even see the tangent anymore. It's off the screen, and it's not hard to imagine what's happening to the tangent as I make the angle exactly equal to 90, or 89 degrees. The tangent is going off to infinity. But as cosine becomes negative and sine remains positive, the tangent becomes negative as well. So here students should realize a negative value divided by a positive value gives us a negative height. But we still get the magnitude being reflected in the length of the line. Then as we move into quadrant 3, when both sine and cosine are negative, the tangent becomes positive again, with its magnitude growing as the cosine goes to 0. So here students can realize that as the denominator of the fraction is going to 0, the magnitude of the ratio is going to infinity. Now let's add in the secant. First I'm going to show you the diagram, and then we'll go through the questions here. So now we're talking about not just the slope of the red line, but the length of it as well. A very nice 10-minute lesson is why is the length of this line equal to the secant of the angle? Well, if you've covered your trigonometric identities, hopefully they've seen this one by now. And they know that the tangent squared plus 1 is the secant squared. Let's see if we can see that identity show up in this picture. Well, what do we have? We have a right triangle formed by this blue and black line. The other side of the triangle is the turquoise tangent, and the hypotenuse is the red line. Here we have a is equal to 1, b is equal to tangent, 1 squared plus tangent squared. Aha, we know that's secant squared, therefore the length of the hypotenuse must be the secant. And let's see what happens as we move this around. Well, what do we notice? Once again, as the cosine goes to 0, the secant goes to infinity along with the tangent. Both secant and tangent are related because they have cosine in their denominators. Can we make the secant go to 0? What happens if we do this? No, it looks like the smallest value that we can make the secant is 1. And a nice little discussion is why that's true. Why is it that the secant can never be less than 1? Its range is from 1 to infinity, or also negative 1 to negative infinity. And now it's time for the also-rans, the cosecant and the cotangent. Poor old neglected cosecant, cotangent. They never get any airtime, and they just get jealous whenever all the discussion centers around the ever-popular sine and cosine and tangent. But with this tool here that I've created, we can add arbitrarily many ratios to this picture. So I've taken out tangent and secant for now and put in cotangent and cosecant in their places. And now we have this picture. And now I invite you, the listener, to try to figure out why is this length representing the magnitude of the cotangent function, and why is this length representing the value of the cosecant function. I'll leave that as a little exercise for you. It's actually quite fun. I think you'll enjoy doing it. But let's see what happens as the angle starts from 0. Well, first of all, when theta is 0, we see that both the cotangent and the cosecant are infinity because they have sine in the denominator, and sine is very close to 0 at this point. As we increase the angle, they become smaller. We can make the cotangent shrink to 0, and I invite both you and the students to think about why that's possible. but we cannot make the cosecant equal to 0. It cannot go less than 1. No matter what we do, its minimum value is 1, and it shoots off to infinity. And here we want to study the ratio. Why is it that 1 divided by the sine can never be less than 1 in magnitude? And now, at this position, if you haven't yet taught this identity yet, this is a perfect place to introduce it. We math teachers know that the cotangent squared of an angle plus 1 is equal to the cosecant squared of that same angle. Very similar to the tangent squared plus 1 being equal to the secant squared. Oftentimes we don't teach this one at all, but this picture is a great place to see it. Let's identify it now. We have a right triangle formed by the red dashed line, the cotangent, and the cosecant being the hypotenuse. Remember, the length of this red dashed line is 1, so 1 plus cotangent squared is equal to cosecant squared. So there's another way to use an animated diagram to discover a new identity. And now, just for fun, I like to do what's called the dance of the 6 trig functions. Behold the elegant ballet of the 6 trig functions as we animate them all at once and just turn them loose. So I'm going to take this animation here and play it in a loop so it repeats itself. Slow it down a little bit so you can appreciate the full beauty of what's happening. And let's see it go. Even if you don't know a thing about mathematics, this is just beautiful. Each ratio doing its own choreographed steps, yet intricately connected to all the others, just like a perfect dance is supposed to be. This is why we teach mathematics, because it's not only useful, it's beautiful, and it's elegant. This concludes my illustration of how to use dynamic animations in Maple to teach high school mathematics, and I look forward to hearing your questions in the question and answer session.
Welcome to the presentation on Building Better Math, engaging high school students with math from real life. My name is Scott Hagan from the British Columbia Institute of Technology. Every math teacher has heard the question, why do we need to know this? And it's often very difficult to rally the resources towards a satisfying answer. As a result, students can end up seeing math as a hurdle rather than as a tool. And since they don't see why learning math is important, they don't choose to pursue math courses, or simply do the minimum required in order to graduate. By the time students become aware of the relevance of math to careers of potential interest to them, years of inattention to math may make the road to getting back up to speed an arduous and expensive one. Many students entering programs at BCIT have had to upgrade their math in order to gain entry to a program they're interested in. In BCIT's math department, we teach into a wide variety of programs, for which we provide targeted math classes. We teach only the math that's necessary in each specific discipline, and that gives us the opportunity to teach math based on applications from real life. Students are often surprised by the number and variety of math applications in their field, and they can get pretty charged about them. The applications engage and motivate the students to learn the math required to solve a problem. By exposing high school students to the same kind of rich applications, we can show them that math is essential in a wide variety of interesting technical careers. In addition to increasing their motivation to study math, applications give students the opportunity to learn about technical careers that they might not have been aware of. Careers in, say, geomatics, nuclear medicine, or electroneurophysiology. And this may spark an interest in a career path they might not otherwise have considered. Most teachers, however, don't have the time or background to research and develop applied problems in a wide variety of specialized technical disciplines and industries. The math department at BCIT is uniquely qualified to present math in this kind of real-world context. Our faculty include physicists, chemists, and computer scientists, as well as mechanical, aerospace, civil, biomedical, and electrical engineers. That's a wealth of expertise that we can draw on in order to showcase ways in which math is useful in many different and broadly ranging careers. The platform that we selected to deliver the database of problems was MapleTA, a product that we had already been using extensively in our own classes. MapleTA allowed us to design questions without compromising the sense of them being truly related to the real world. Questions can be presented in visually interesting ways that not only engage students, but also clarify the connection between the math and the real situation under investigation. The Building Better Math database was designed to present students with rich applications having the look and feel of real life. Yet each problem requires only high school level math to solve. Any additional information that's required in order to understand the application is provided right in the problem. Let's take a look at several of the features of Building Better Math. Thanks to randomly generated values, each student's assignment is unique, but still consistent with a realistic problem. This gives students the opportunity to discuss how to solve the problem rather than what the answer is, and they can therefore learn from each other. Where applicable, graphs, images, and animations are keyed to the same random variables, so each student's assignment is fully personalized. With every student's problem being different, the workload for teachers would clearly be prohibitive if the problems were not graded automatically. At the discretion of the teacher, students can be allowed to check whether their answers are correct or not through a feature called How Did I Do? This gives students a chance to correct errors as they work. The automatic grading and the How Did I Do feature give students feedback at the moment when it's most relevant to them, and most likely to allow them to improve their skills. Students can take assignments as many times as they want without adding to marking. And full solutions are available for teachers, and these can also be made available to students. Assignments are always available. They can be completed online or printed for offline access. Working offline allows students to work on problems that require some development. They can work on that on their own, in small groups in which they discuss their solution strategies, or as part of a class project. This makes it a tool that can be used not only in the computer lab, but also in the classroom, and even at home. Questions from the database are sometimes used as a hook to catch the student's interest at the beginning of a unit and explain why the math they're about to learn might be useful. Or they could be used as a wrap-up to challenge the students to apply what they've already learned towards the solution of a realistic problem. The Building Better Math database is hosted by our partners at Maplesoft, so there's no server setup or administration to worry about. All that is required is internet access. The database currently contains ready-made assignments for each major topic in a typical grade 10 curriculum. While these assignments have been developed on the basis of the WNCP math curriculum, the Western and Northern Canadian Protocol, most high school math curricula would cover the same topics. The ready-made assignments can be used as provided or modified by teachers to best suit their needs. Future releases of Building Better Math will have similar ready-made assignments at the grade 11 and 12 level, but the content for those grade levels is already part of the database. Teachers can easily search the database to compose their own assignments, customized to the difficulty level and topics they're looking for. Now, let's take a look at the interface and a few sample problems. When you or your students log in, you'll be taken to your class homepage, which will look something like this one. Any assignments that you've posted will appear in the list. By default, you'll see 2 practice assignments, one to get your students used to entering their answers, and another to give them some practice with the unit conversions that frequently arise in realistic problems. Now we'll take a look at a sampling of the problems in the Building Better Math database. This first problem relates to the renovation of a community hall in a northern municipality. Logs are to be erected down the center of the hall, and students are asked to determine what length must be cut off each log in order to swing it into place without gouging the ceiling. Animations help the students understand the problem and where in the process of swinging the log into place they should focus their attention. The next problem comes from the Functions and Graphing section and presents students with a graph comparing average body mass index in 4 countries. The graphs and the countries involved will be completely different for each student. The students answer a series of questions that test their understanding of what the graph communicates and ask the students to make a numerical determination of an average slope. From the Geometry section, we have a question related to rivets. Students are provided with clear diagrams to help them understand the vocabulary and some animations to show them how the shape of the rivet changes when the shank is flattened. They are then asked to determine the maximum thickness of metal that a particular rivet can be used to fasten. As in every problem, each student receives different numbers within a realistic range. In the next problem, students will determine the distance between a seismic observatory and the epicenter of an earthquake. They are first guided towards developing the system of 2 equations in 2 unknowns that they will need to solve in order to make this determination. Notice the "How did I do" feature has been activated in this assignment so that students will be able to check whether their answers are correct or not by clicking on the link in the upper right-hand corner of their screen. This next question, which comes from our trigonometry section, comes from physiotherapy. In the aftermath of elbow surgery, a patient needs to strengthen her bicep, but it is important that the elbow joint not be subjected to too much force. Students determine what force will be exerted on the elbow if the patient lifts a particular weight, and whether or not this exceeds the allowable maximum. In our logs and exponents section, students explore the increasing acidity of the world's oceans and its relation to atmospheric carbon dioxide levels. All the knowledge of chemistry that they require to answer the problem is related directly in the question. And finally, for new or potential drivers, we have a question related to police radar. Students are asked to make corrections to the police radar measurement that arise from the fact that the police cruiser must be positioned off the road rather than directly in the path of the oncoming vehicle. Ultimately, they will determine whether the driver should be ticketed or not. For more information about Building Better Math, visit our website at www.bcit.ca/bettermath. I hope you've enjoyed the presentation and that you enjoy the rest of the event. please contact Maplesoft if you would like to get in touch with me for more information.
That concludes the session. Thank you for joining us today. Please don't forget to visit the Communication Lounge to ask any questions you may have. A recording of this presentation will be archived, and you will be notified when it's available.